stopped. We had this long break just in the middle of proving something. So let me remind you what we're proving. So it's of course in the generality that I'm considering now is not entirely trivial, but the essential of these. If G is a reductive complex group, complex form in G. So G is complex, so I'm completely identifying between G and its complex form points. And all such are conjugated. So the remark I want to make. We've seen a compact form is a maximum compact subgroup. They are, it is necessary. So a compact form is explicitly not now having G, not thinking in algebraic geometric terms. This is a group, topological group, and a compact form is the same as maximal compact subgroup. Okay, what we've seen, we proved well, it was 2, I guess. That's fine. Now it will be 1. Special case that we proved it in the case that we proved it in case G naught is a torus. So G is a finite extension necessarily here of a torus. Let me remind you, inside this torus, I mean this torus just C star to the n, and it decomposed naturally as S1 to the n times R star to the n. Oh, sorry, R star plus to the n, and if we forget algebraic geometry, then R to the n, taking log. And so if I divide by this characteristic subgroup of it, with the compact torus, S1 to the n, I'm left with a finite extension of Euclidean space. And we've seen that they all have, they're all split. Every such an extension is actually a semi-direct product, so I can find an actual finite group in it that meets every connected component, and the Bray image of this in G of this finite group will be the relevant compact form. Now special case 2. This is maybe, let me call it symmetry. Same for a G connected semi-simple. This we haven't proved. This we need to prove. What I'm about to show now, these two special cases give me a complete proof of the theorem. And this is not a surprise, of course. We know that, maybe, never mind. Connected reductive group is actually a Toe's extension of a semi-simple. Now, everything whenever I'm making algebraic geometric remark or whatever, this is over the complex numbers, of course. Reductive group is of the form always. Well, I have the center of G, and I have the commutator group of G, or the group generated by the commutator. The group generated by the commutator, this is a basic, it's not complete commutator, it's a basic fact of this. The group generated by the commutator is again algebraic, and this is semi-simple, and this is a Toe's. So actually, and of course they commute, one of them is central. So actually, I can form the map, the product map from this, and this map has a finite kernel, which is the intersection of the two. So in our case, okay, maybe I'm ahead of myself. I will say something. So G0, I can always write down as, well, I can take the centralizer of G0, but I should now take it in G0 and G0. So this I will denote Z, C. And this is H. So this is the connected component splits nicely. And of course, then our group G generated by this H and this, well, and I'm left with this, but also I have this finite group that I'm not seeing here. Right. So I will use this to prove the theorem, but now let me develop things. If I would just deal. Oh, okay, let me now make some preparation, which actually I find of interesting by itself. So here's a claim. So again, what I'm about to do now next is to prove that theorem using, well, that means that we already proved, and this which proved this postponed to later. Okay? Later on I will prove that. Now I'm doing some preparation, which is, you might say, unrelated, but interesting. Now H is a complex semi-simple group. K in H a compact form, then I claim that K is its own normalizer in H. So this is a classical piece, and I will prove it. We'll use it in the course of the proof, the main theorem. This will follow from again a nice theorem by itself. So I will generalize this now to more general groups. So this is a special case of a statement which is valid for arbitrary algebraic group, and it is the following. So let me, in your permission, use the symbol G now instead of H, because it's unrelated. Now G algebraic. And K compact, any compact. Then I claim that the normalizer of K over the centralizer of K is complete. So again, the normalizer group is a closed subgroup in G. So now consider this as topological group. It may not be compact, but its non-compactness comes from things that actually centralize, commute with K. Okay. By the way, the normalizer of a non-algebraic K, well, K is the real algebraic group, but it is not a complex algebraic group, right? The normalizer is not a complex algebraic group. It will be a real algebraic group, but not a complex algebraic group. Well, in this term, actually, I'm not assuming it. Well, it's always the case with K is a real algebraic group. But this is not part of the assumptions. Now, but the centralizer of K, to centralize, to commute with something, is a Zariski closed condition, right? So, note, if I'm commuting with elements of K, this is just the intersection of things in G that commute with each element of K, right? Each of those guys is whatever commutes with like some little K is an algebraic piece. And what I'm trying to say is that this is the same as whatever is commuting with the closure of K.
So this is always algebraic.
So I'm saying that this piece is always algebraic, and actually, this group W. So W, never mind. W is could be seen as a subgroup of the algebraic group take the basic closure of that one and divide by this basically closed sum. So this is the algebraic group, and this is the natural host for this thing, and in this guy, this one is compact. This is the claim. Okay. So that statement is clear. Let me make one more reduction. Okay, I will erase the main term that we're proving. I hope we'll not distract what we're doing. And maybe So I should have said that this is clear, that this implication is clear, right? So I'm not proving this, I'm proving that. And yet another reduction. So theorem. Now, G as above. Act on an affine variety. And now, take K, I'm using the same symbol, but now K is in V. This is a compact subset. So in the generality I'm considering now, I'm not assuming that even that K is a group. And
Why is the implication clear?
Because of K here, this is a compact form, and I just arranged the remark over here that it is a risky dance. And so the whatever centralizes K centralizes everything, right? So this is the center of G itself. But in the theorem that we are proving, G is semi-simple. So it has, well, yeah, okay. So it has a finite center, and so this piece is finite. So if the quotient is compact, also that piece alone is compact. Okay, so that's about this implication. Is this clear? So I use the fact that in the claim, what is different from the claim and that general theorem? I mean, that's the same. Only here, actually, what I wanted, the only thing that I wanted, to prove is here, is that age has no center, or finite center, or compact center, which is the same because they're over the compact groups are finite. Okay, theorem. Now I'm acting on an affine variety, and I'm having whatever compact subset. Then the claim says that I can look at two things. The pointwise stabilizer of K, the fixator of K, and the stabilizer of K as a subset. I'm using those two symbols. These are the standard ones. This is the subgroup of G that stabilizes K as a subset. Usually, I mean, it's a closed subgroup of the house of topology, but usually it is not an algebraic group. And this is the fixator in G of K. Again, this is the intersection of all the elements of G that fix every pointer in K. So this is which each of these guys is algebraic. So this is an algebraic set. Same markers here. This is the same as stab G K over G, which sit naturally inside the vantage point. Now, why is that? Well, is the affine action that I see here? Conjugation action of G on itself. G is an affine variety by itself. It acts on itself by conjugation. So V is G, this action is the action by conjugation. K, in that form, I might view as just a subset of that variety. And the interpretation is clear. The normalizer is exactly the stabilizer is the fixator.
The statement is compact.
And is compact. I guess I should have written it down. So, there is a statement here. This is a remark. Thanks. So are we clear? Are we clear? Now, this is a very general statement. It is valid over arbitrary local field, actually. I'm thinking of the complex numbers, doesn't matter. This is true over arbitrary local field. And in fact, over arbitrary field with absolute value. Also, I can replace the notion of compactness by the notion of boundedness, which is more natural over non-local fields. Get a similar result. You will see the proof. The proof is very big. So I'm proving the last term. And well, let me make some reductions. So everything. So the statement is about the compactness of this topological space. This topological space lives in that algebraic group. So actually, I may assume a priori that G is just that, right? G does. I have no interest in G here. I have interest in the compactness of some subset, right? So G is some algebraic thing. So I may replace G by this. So let me write this. But this is not the we may replace. This is not the last thing. G with stub G. So we may assume that G is the recent closure of the stabilizer of this K. We may replace V. I have no interest in everything that happens in V. I have interest only in the part that C K, right? I want V to be an affine thing, but I can just take this piece here, the Zariski closure of K. This is a Zariski closed subset of V. Everything lives inside it. This is actually stabilized by my new reduced G. So it is fine. I can reduce to this one. So V with and it's not the last thing. Now on this piece, on this new V, this group, the fixator of it are trivially. So the action of G is not faithful, and so I can mod it out, and assume by modeling it out, again replacing G with the quotient that fix V, fix K. Is trivial. So I will not prove compactness of the quotient. I will prove compactness of something in G, the normalizer itself. We do so. Now we are almost there. Now there is a fact that I hope you remember from your basic algebraic group course. Fact, very convenient fact. Some of you are smiling. G algebraic, V affine, G act on V algebraic action. This is the setting that we have. Then I can linearize it altogether. Exist vector space over the field of definition here, which is a complex number in our case. E representation, algebraic homomorphism, G to G and E, and equivariant embedding V to E. Equivariant with respect to the action of G here and the action of G and N here, and the map. So I can assume that everything is happening inside some vector space. Why is that? So this is a very, very general fact. As you see, maybe
Finite dimensional?
finite dimensional. Yeah. So here is the one of the most basic facts that we see in the first few weeks of a good course in algebraic group theory, is that inside Kg, and maybe I already reminded that, inside Kg, or inside actually Kv in that case, G act on Kv, and so this is some infinite dimensional vector space on which G act, but it's locally finite as a G representation. Every finite dimensional subspace is contained in a finite dimensional G invariant representation. Why is that? Basically, because we have this action map, KV and KG, use finite generation. Well, it's very basic, and I'm not reviewing that one. I'm just very vaguely, I will tell you the recipe how to construct this E. This is finitely generated. So take the generators. They are functions of V, F1 to Fn, right? And take E to be a space generated by those, which is G invariant. And those Fs give you naturally, you can interpret those as some embedding of the E. Okay, so okay, we have this one. We're almost there. So we take V to our space E. So basically, I'm using this fact to assume that our situation that we want to prove in this theorem over here sits inside some vector space, and K is we use this fact. We use this fact, assuming as we may that V spans E. So of course, whatever V is G invariant, so whatever it spans, subspace it spans is V invariant as well, is G invariant as well. So I can just reduce, I can take that piece of E to be my E. And the image of K, the first compound. And invariant under nomad or the stack. So the latter. Must be compact. Or maybe I guess I'm using the fact that I have no room anymore to write down, so I just say it. This must be an injection, right? Because I mod out by the fixator. So this is an injection, as is happening with homomorphism for by groups. The image is closed. So G is actually homeomorphic to its image. So this is a non-trivial, very useful statement. But we know it, and so the image is closed means that it's enough for me to show that this is compact in the image, right? This will be a homomorphic image of that one, and now it preserved a compact spanning subset. Why spanning? Because K is the risky closed, the risky dense, excuse me. The risky dense in V, and V spans. So K must span. This group here stabilized a compact spanning subset, so it stabilized some norm. The norm generated by this compact thing, and G must be compact. And not G, each piece. Okay? So this is, again, we proved this, which is a very useful fact, and the interpretation for applied groups is the almost compactness of normalizers and compact things.
Can you repeat the last value? There's a norm.
Yes, whenever you have a compact set, you can cook a norm out of it. Well, a compact spanning set. What will be, well, first you symmetrize it with respect to 2 minus, and you declare, like, do you know Minkowski function in function analysis? I don't know. This is a norm.
Yeah, but why how do you do this compactness of the...
There are many ways to reduce the compactness of this thing, but I use the fact that it preserves, in my oral explanation, I use the fact that it preserves a norm on the vector space E. And so whenever you have a compact spanning set, whenever you have a compact, whenever you have, a compact set.
This norm thing doesn't have to be doesn't something have to be convex?
So, when I say it induces a norm, you take the convex half of it. You symmetrize it, and you take the convex half of it. Somehow I didn't want to use the term convex half, because if you do the exact same over another local field, not the complex numbers, then you do slightly. You don't have convexity, right? But you can play around with it. At this point, if you stabilize the compact spanning set in a vector space, this is easy to see that you must be compact. So I leave the details as an exercise. But since we are over the complex numbers, and in fact we are over the reals by the restriction of scalars, right? I mean, I'm dealing here with topology. So this is, we may regard here E as a real vector space and forget complex numbers, and we have here this compact set, and we take the convex half of it, the symmetric convex half of it, and this is a ball for some norm, which must be preserved under whatever is preserved.
Okay. Linear.
Sorry?
You have to use somehow that the action is linear. So
yeah, the action is linear. No doubt about it. I'm using it. Yes, I didn't forget everything. Fine. Where are we in time? When are we? Okay, so this is just preparation for proving that semi-theorem implies theorem. Yeah, and we will use that. We don't need these anymore. We have the claim. So now, again, we look at a general. G is a reductive group. This is the setting. Proof of main theorem. Main is the one that I stated at the beginning of this class. We're proving the main theorem. We will use everything that we stated so far, and again, we will have this hope of proving this later on. So G is a reductive number. G0 splits to be the product, almost direct product, of Z and H semi-simple, Z a torus, and there is some finite noise over there. That is not on the picture here. And oh, I guess there is a corollary here that I forgot to state. Yeah, I will use this one, sorry. Corollary from whatever we did before. H semi-simple connected K compact form. Then this is a corollary of that thing. The space of compact form of H. Look at all compact forms of H. They're all conjugates of K itself, right? So look at H act transitively by conjugation on the space of all compact form, maximal compact subgroups of it. What will be the centralizer of each? When H acts on some subgroups of it, the stabilizer of a given subgroup is the normalizer of that given subgroup. So it's a corollary of that thing, of course, of that theorem. It looks like H mod K. Okay. Now, this is some characteristic space of H. If H happens to be normal in some G, which is the case here, right? H is a characteristic subgroup of G0 and of G. Then G acts on H by conjugation, it preserves H, and it takes a compact form to a compact form. So it acts on this space, transitively of course, because its subgroup H already acts transitively. Okay? So I'm taking, to begin with, take a compact form of H. Again, of that H. And now I want to look at the normalizer in G of that K. Or maybe, I don't know, the word before, G acts on compact forms of H on that space, whatever structure you give on it. The stabilizer of K itself being the normalizer in G of K. H acts transitively, as we said here.
I'm proving the corollary.
No, I'm not proving it. The corollary is the corollary of this claim.
Yeah.
Sorry, this
But
is
it
proving the
looked
main.
like
No, I'm using the corollary. But maybe I'm repeating myself a bit.
G is H or G is something else. I'm confused.
Sorry, because I zigzagged a bit. I should have started this only after stating. This corollary is a corollary of this claim and maybe the semi-theorem alone. Proof had not started yet. Now the proof starts. Now G is reductive. Now we have this decomposition. Now H is semi-simple. Now we take K to be a compact form in H. And you consider all compact forms in H. So this is just a basis point in that space, which is a copy of H on K. But this is a G space. G acts on it, and this is the stabilizer in G. So I'm using it in order to get some decomposition of G, or some presentation of G. Here it is. I claim now that G, every point in G, take the base point K somewhere else, which I can take back by H to this, and get something in the normalizer. So I claim that H decomposes like that. Every element in G. Every element in G can be written as an element in H times an element here. Of course, not uniquely. The non-uniqueness is given by some element of K. I mean, the intersection of these two is K.
So you had to have that claim for that?
I use the fact.
Isn't it just...
No, here I didn't use the fact that the normalizer of K. Sorry, I did. I use the fact that space of compact forms is H mod K, not H modulo the normalizer in H of K. Otherwise, here I would take the normalizer in G of the normalizer in H of K. But the latter is K.
Oh, okay.
Okay. So I already used the preparation that we had, but I will use it in a more substantial way in a sequence. Okay, now let's consider this guy over here. What is his Zariski closure? Well, of course, even before taking the Zariski closure, under the line, this is just the same as that. I mean, K is a subgroup of that, obviously. So and now I'm taking something smaller, take the Zariski closure only on K, and leave this guy alone. And I know what the Zariski closure of K is. What is the Zariski closure of K? No, that was before. That was not H. So K is a form of H. So it's dense in H. And this is H as a normalizer. And this one is G. And for this in G. So everything here is eventually. So you get that this one is dense. Good. So that was a corollary. Now I'm about to.
So in the last step you want to use the claim, right? But K is a compact form of H, not G.
K is a compact form of H. The normalizer, this normalizer is not compact, right? What is my mission? My mission is to come up with a compact form for G. I want to find something compact in G, right? Compact and dense. Now, this is pretty much close to be compact. It is not compact, it's a compact module of some centralizer. It's almost compact. And it is dense. This is what I want. So I'm getting closer.
So I think you still didn't use the claim.
I used it as you remarked.
No, but so again, G acts on the compact forms of H anyway.
It acts anyway.
And
But what will be the stabilizer of a compact form? Yeah, so let's yeah, I didn't use it. So I didn't.
Still no use.
Still no, I still haven't used it, but I will. Yeah, I'm sorry, I got only confused in my notation and thoughts. I still haven't used it. I will use it pretty much soon, pretty soon. Okay, now we have, again, our game. Our goal is to find a compact Zariski dense piece in G. We find something in G, which is Zariski dense. It's the normalizer of K. It is not compact, but it's not that far from being compact. Somehow, case 1, which was here, the raise now, will help me to extract something which is compact in it, right? Because the structure of this normalizer is pretty close to be a finite extension of the topos. Or this modulo K. Let me explain. Where am I? Consider now, just for a minute, only the stabilizer or the normalizer in G0 of K. What is that? G0 as its center and H. In H, what normalizes what normalizes K is K itself. And in the center, what normalizes K is everything, right? Because it's central. It's centralized, actually. So this is the whole Z thing times K. And since this is, of course, this is finite index inside that, so yeah, is finite index in identify now the normalizer okay, we may identify, maybe something which is slightly illegal, so let me remark on that. Take this one, or take that one, to be precise, and divide by this, of course, normal subgroup of it. Now, I took something which is not algebraic and divided by something which is not algebraic, but up to a finite index, this is like taking zk over k. So with an algebraic group, I'm not writing it down in an obvious way. So if I'm looking just on the connected component of this piece, this is just z modulo the finite group, which is the intersection of it with k. In an obvious way, because I do want, this is, I do want to say that after dividing this by k, I'm back in case 1. This is this group as torus identity component. Right? It's a finite function of Z. Hence, by case 1, a compact Z-dense sub C. So C. Maybe I can phrase it in some more pedantic way, but I hope the argument is clear. And the thing is that if you wish, by the way, I don't have to retract to case 1 if you're not happy with the way I put it. I don't have to retract to case 1. I can just repeat the proof of case 1 for this. The proof of case 1 was not about algebraic group. So this thing over here has a piece of Z in it, and it has some compact torus in it. If you mode it, you will get a finite extension of an Euclidean space, and it splits, blah, blah, blah. Okay? And so I can find this C, and now I claim, so the plane image of this C will do the job. This is something that will contain plane image. Inside here, it will contain K, but also it will be dense in this Z, and so it will cover the Zariski closure will contain the Zariski closure of this thing. So it will contain H as well, so it will contain all G0, and it meets every connected component of G. By the way, I constructed it. So the plane image of C in NGK is compact by compactness of C and K. It's the closure contains both Z and both Z because this is the way C was constructed, and H because K is a Zariski dense in H, and H and contains G0 because this one is the product of the two, and meets every component of G. Again, by the construction of C. By basically our cohomological argument, by the splitting argument, if you want to track back where it comes from. Hence, it is a compact form. אני רוצה להגיד משהו נוסף לפני שנתפזר אישי של דרכו, כי אחרי זה נמצא לכם משהו אחר. So I'll take some time so we didn't finish the proof yet. We prove existence, but not uniqueness after conjugation.
We still have the sanity.
Sorry?
We still have the sanity.
Of course, we still have the sanity to prove. And we will do it, at least I will sketch it in the next hour. But before, I want to come clean to this. the next hour. So let me finish. Or maybe I can let you sum up. So just remember, for the next hour, we proved the existence of the compact form. We didn't prove uniqueness, and in fact, I will not prove it. I will explain where it comes from, and we will get to it later, to the actual proof. So our proof will not be complete in any case.